Welcome back to the classroom. Today we're going to have a look at the second lesson in chapter 10. We're going to have a look at two topics. They are single-slit diffraction and the diffraction grating. Okay, imagine we shine a beam of light through a wide enough opening. We might expect the beam to pass through with very little diffraction. However, when light passes through a progressively narrower opening, the wave properties of light often produce unusually looking patterns, such as the diffraction pattern shown here in figure 1. So in this section, first we'll have a look at the formation of such diffraction patterns. Okay, so let's have a look at the concept of single-slit diffraction first. To understand how a narrow opening, for example, 100 μm wide, can affect light passing through it, consider the behavior of light passing through a single slit, which is here, as shown in figure 2a. Okay, let's have a look at the figure on the very left here. This is a basic setup of single slit diffraction. While investigating this configuration, we assume that the following conditions exist. So be careful with the following assumptions. First, the width W of the slit is narrow enough that a substantial amount of diffraction can occur, but not so narrow that it acts as a single point source of waves. Second, the light source is monochromatic with a wavelength lambda. Third, the light source is far from the slit, so that light rays that reach the slit are all traveling approximately parallel to each other. Such configurations produce Fraunhofer diffraction, which shows a bright central fringe called the central maximum. The central maximum is flanked by dark fringes called minima, and less intense bright fringes called secondary maxima, which is shown here in figure 2c on the very right side. So why do these fringes occur? And how can you predict where bright fringes and dark fringes will appear on the screen? The key to answering these questions is Huygens principle. Okay, recall from the previous chapter that Huygens principle states that each point on a wavefront acts as a new source of waves, right? So here, figure 2b is a magnified view of the slit, looking down on it from above, showing its width. According to Huygens principle, all points across the slit west in figure 2b act as wave sources, and these different waves create an interference pattern at the screen. So when the slit is divided in half, which is shown here, upper half and lower half, when it's divided in half, coherent waves that interference with each other appear as a light passes through the slit. The points in one half are labeled A, which is these points here. And the points in the other half are labeled with B, B1, B2, B3, and so on. Each of these points is a source of Huygens waves, or spherical waves, including point A1 at one edge of the slit and the corresponding source point V1. Okay, A1 and B1. at the center of the slit. Okay, figure 2C shows the distances from these points to a point P on the screen. The path length difference, path length difference delta L is here from this point to this point. Although figure 2 shows the screen close to the slit, assumes that the screen is quite far away. So all the angles denoted by theta are approximately equal. Okay, next, suppose the waves from A1 and B1 interference destructively when they reach a particular point on the screen here. The path length difference is then given by delta L, which is here, should be lambda over 2, which is a half of lambda, right? Because the interference destructively. So the length difference must be a half of the wavelength. So when this condition for destructive interference is met for points A1 and B1, the waves from A2 and B2 will also interfere destructively, which is for A2 and B2, right? Because they have the same length difference with A1, B1. As well as waves from A3 and B3 and so on, for all similar pairs of points within that slit. Destructive interference produces a dark fringe on the screen. From figure 2C, you can see that delta L equals, okay, let's consider this right triangle here. Delta L is a half of W times sine theta, right? Where W is the width of the slit. Okay, next we can, because we have these two relationships, we can substitute a half of lambda for delta L, that leads to half of W times sine theta n equals lambda over 2, which actually gives the angle of the first dark fringe on one side of the center of the screen. On the other side, the corresponding value gives the angle of the first dark fringe to that side of the center. So the first dark fringe are thus at the angles in which we have this relationship. W times sine theta 1 equals lambda. This gives us the first dark fringes. Okay. Okay, next, let's have a look at figure 3. This figure shows the method of determining the position of the second dark fringe. In figure 3A, which is on the very left, the slit is divided into 4 regions. The points in these 4 regions are denoted by A, B, C, and D, respectively. Figure 3B, which is in the middle, shows the path length from the farthest point in each region, A1, B1, C1, and D1, to point P on the screen. Here. Suppose the path length difference for Huygens waves from A1 and B1 is delta L equals 1/2 of the wavelength lambda. So delta L equals lambda over 2. Have this relationship. So these waves interference destructively, right? The path length difference for C1 and D1 has the same value. So these waves also interference destructively. The path length difference is the same for waves from other pairs of points A2 and B2, C2 and D2, and so on. So these waves also interfere destructively, resulting in no light. or a total intensity of 0 on the screen. Thus, for the second dark fringe, which is here, second dark fringe, we have delta L equals a quarter of W times sine theta. Setting this expression equal to 1/2 of the lambda, then we have the following relationship. The interference condition in this case is the following, where the angle again corresponds to fringes left and right of the center of the screen. So lambda times sine theta 2 equal, W times sine theta 2 equals 2 lambda. This is the relationship of the three variables in the second dark fringes. Also, we can use the same method to predict the third and other dark fringes by dividing the slit into 6, 8, 10, or any even number of regions. The result for the nth dark fringe is given by this relationship. Okay, W times sine theta n equals n times lambda. This is a relationship of the three variables for the nth dark fringes. Okay, where n equals 1, 2, 3, and so on. The values of theta n that satisfy this equation gives the angles of all dark fringes. You follow me? Okay, next, to determine the angles for the maxima, we use a similar method of dividing up the slit. For maxima, however, we divide the slit into an odd number of regions. Light from all but one region will interfere destructively, as in the discussion for minima, and the light from remaining region provides the maximum. So to calculate the first maximum after the central peak, which is here, okay? This is called the first maximum after the central peak. There are two of them. We use a similar method. Divide the slit into three regions. For example, in the equation for destructive interference of two of the regions, the effective slit width for each region is a third of W. Then we have the path length difference is a half wave length as always. The location of the fringe is given by this formula. A third of W times sine theta equals 1/2 of the wavelength, right? This is a relationship between among the three variables in the first bright fringes. You can calculate additional bright fringes by breaking the slit into 5, 7, or 9, or any odd number of regions, right? The result is that maxima occur in general when we have this relationship. W times sine theta m should equal m plus 1/2 times lambda, where m equals 1, 2, 3, corresponds to the first, second, and so on bright fringes. And the values of theta m that satisfy this equation gives the angles of all bright fringes. All right. Okay, next, let's have a look at figure 4 here. Figure 4 shows the intensity curve for single-slit diffraction on the screen. For each successive bright fringe, more of the slit acts as point sources of light that interferes destructively. The intensity of bright fringes, therefore, decreases away from the central peak. You can approximate the width of the central bright fringe by using the angular separation of the first dark fringe on either side. We can calculate the angles for these dark fringes by setting n equals 1 to obtain the following relationship. Line theta 1 equals lambda over w, right? Okay, so here on the top left, figure 5 shows the projection of the fringes on the screen. The distance y1, which is here, of the first minimum from the central maximum is then y1 equals L lambda over W. So here, because L is very long, we can use approximation that sine theta is approximately tangent theta. So sine theta here is approximately tangent theta. Okay. The width of the central maximum is the distance between the first minima, or 2 times y1, or 2 delta y. 2 delta y is then 2 times L lambda over W. Then we have delta y is L lambda over W. The separation of the central maximum from the first minimum, 2 delta y, is half of this, or just y1, which gives us the wavelength. If you know the values for W, delta y, and L, then we can calculate the wavelength of the light, right? Lambda equals W delta y over L. From the equation for the location of the minima, the distance from each minimum to the next one is also y1. You can observe this from figure 4 here. This is useful for predicting the positions of the fringes and the wavelengths of light from the diffraction pattern. In particular, a longer wavelength or a smaller width produces a larger value of delta y and a wider diffraction pattern. So figure 5 also shows the angles for the single-slit diffraction pattern. By determining the angle and distance from the screen, you can calculate the distances between fringes. The following, okay, I'm gonna show you a tutorial following this model here to illustrate how this knowledge can be applied to solve problems, okay? But here, first of all, I'll give you some time to have a look at this model here. All right, next, let's consider this question. Light with a wavelength of 5.4 times 10 square nanometers is incident on a slit of width 11 μm and produces a diffraction pattern on the screen located 80.0 centimeters behind the slit. Can you calculate the distance of the first dark fringe from the central maximum on the screen using what we have learned so far? Okay, I'll give you 5 minutes to have a look at these questions, and then we'll have a look at the solution together. Okay, you should be able to finish this very quickly, right? So according to the previous model here, we have delta y equals L lambda over W, right? We can directly use this formula to calculate delta y. This question actually asks you the value for delta y, right? Or y1. Okay, so using this formula, we have delta y or y1 is L lambda over W. We know L, we know lambda, and we know W. So we have delta y equals 3.9 times 10 to the power of -2 meters. So the first dark fringe is 3.9 centimeters from the central maximum. Okay. Any questions? All right, then let's consider another one. So in this question, we have a light with a wavelength of 670 nanometers, which is incident on a slit of width 12 μm, and produces a diffraction pattern on a screen that is 30.0 centimeters behind the slit. There are three questions you need to answer. First, calculate the angle, calculate the angular width and the absolute width in centimeters of the central maximum. Second, calculate the distance between the first and second minima. Then, determine the distance between the second and third maxima. Compare this answer to your answer in B. Does this answer make sense? Explain why or why not. Okay, you can start now. I'll give you 5 minutes to consider this question by yourself. Okay, now let's have a look at the solutions. Okay, in question A, we know sine theta 1 equals lambda over W, right? The distance from the central maximum to the first minimum on each side is given by y1 equals delta y. The angle for the first minimum is sine theta 1 equals lambda over W, where n equals 1, and the angular width is 2 theta 1. So to calculate 2y1, we can use lambda equals W delta y over L. We can directly use the formula here. So first of all, sine theta 1 equals lambda over W. This gives us sine theta 1 is 0.05583. So theta 1 is approximately 3.201 degrees. So the angular width of the central maximum is twice of this value, which is approximately 6.4 degrees. On the other hand, 2 delta y equals 2 times L lambda over W. And this gives us 2 delta y is approximately 0.0335 meters. That's the absolute width of the central maximum, which is 3.4 centimeters, right? Okay, in question B, we want to find half the width of the central maximum in question A, right? Which is actually y1. So y1 equals 2 delta y over 2, which is actually delta y, right? We have here, twice of delta y is 0.0335 meters. So delta y is approximately 1.7 centimeters. That's the distance between the first and second minimum, which you can see here from this model here, right? The distance between the first and second minimum is here. First and second minimum, which is also delta y. Okay, next we want to find distance between the second and third maxima, which is, as you can see here, the distance between the second and third maxima, which is here and here. Still, this value you should expect this value this value is delta y again, right? Okay, so this is still half of the width of the central maximum in A. Therefore, we have this value equals y1, which is again 1.7 centimeters. The distance between the second and third maximum is 1.7 centimeters. Answers B and C are actually the same. This makes sense because the distance between adjacent maxima is identical to the distance between adjacent minimum because the pattern is symmetrical, which is shown here in this model on the bottom right. Okay. Any questions? All right, then let's have a look at another related concept, which is called resolution. The resolution of an optical device is the device's ability to separate closely spaced objects into distinctively different images. Light passing through a small opening is diffracted, and smaller openings produce greater diffraction. When light from two objects passes simultaneously through the same opening, the light from both sources is diffracted. It produces overlapping diffraction patterns, and the images appear fuzzy. If the opening is quite small and the objects are close to each other, distinguishing between the two images can be quite challenging, which is shown here in figure 6. So in a summary, the resolution is just the ability of an optical device to separate close objects into distinct and sharp images. So as you can see here, with large opening, the images from two light sources are fuzzy, but distinguishable. With a smaller opening, the images can overlap and are difficult to distinguish. So in many optical devices, a small lens replaces the opening. The resolution of the device is then the ability of the lens to form two sharp images. When light passes through the lenses, the diffraction leads to a single bright spot surrounded by concentric circles in a diffraction pattern called airy disk, which is shown here in figure 7. Two small objects will each produce an image surrounded by diffraction fringes. If the bright parts of the diffraction pattern for the first image fall on the dark area of the other image, the two images may be inseparable. Lenses and openings that are small relative to the wavelength of light usually produce lower resolution images by increasing the effects of diffraction, as seen here in figure 8. But factors other than diffraction affect the resolution of lenses, such as those on cameras. So as you can see here on the bottom right, when the resolution of an optical device is not sharp enough, stars that are in close proximity appear blurry. Whereas in figure 8b shows that when the resolution is sufficient, more individual stars can be clearly seen. In an ideal set of optics, 84% of the incident light is concentrated in the central maximum. If there are obstructions in the optical path, such as a mirror, more light will end up being spread into the rings, making the image less clear. This principle makes a refracting telescope the sharpest theoretical optical instrument for a given diameter. A refracting telescope uses a lens with no obstructions in the optical path. Reflecting telescopes use mirrors instead of lenses, but they often contain more than one mirror in the optical path. Optical telescopes have small diameter objective lenses. Due to diffraction, the best optical microscopes can typically achieve a magnification no greater than 1,000 times. One way to improve resolution is to use shorter wavelength light. Therefore, an ultraviolet microscope can achieve a much greater resolution than one that uses visible light. Most observatory telescopes use curved mirrors, which is shown here in figure 9. Astronomers use the telescopes with the largest mirrors to view the most distant objects, not only because they collect more light,
You have two students here who are not in the course, but they sit in.
Yes.
Word.
Yeah.
Like,
Okay, we just talked about astronomers use the telescopes with largest mirrors to view the most distant objects, not only because they collect more light, but also because the large apertures reduce diffraction effects and offer greater resolution. Okay, so that wraps up this first half of today's lesson. We can take a 10 minutes break, and after that, we'll have a look at the second half, which is about the diffraction grating. Diffraction grating, sorry. Okay, next, let's have a look at the concept of diffraction grating. It is difficult to measure the wavelengths of light accurately because it's difficult to measure the wavelengths of light accurately using the interference pattern from either a double slit or a single slit. The interference pattern may be dull or the resolution fuzzy. To solve these problems, most researchers use a diffraction grating, which is a device that has an array of many parallel slits. White light is a mixture of light of different wavelengths, so as it passes through the slits in the diffraction grating, the waves originating from the slits interfere. The interference produces light of various wavelengths that travel along different paths, which is shown here in figure 1. This creates an effect similar to passing white light through a prism. Okay, let's have a look at the diffraction gratings. There are two types of diffraction gratings: transmission gratings, which transmit light, and reflection gratings, which reflect light. CDs and DVDs are common examples of reflection grating. When illuminated, they both produce iridescent reflections. A transmission grating, however, usually has an anti-reflection coating. Transmission gratings are typically used in spectroscopy. Most of the discussion here concerns transmission gratings, but the same concepts apply to both types. The process of manufacturing an effective transmission grating involves precision machinery. One method uses a diamond tip to etch closely spaced parallel lines on the grating surface. The lines are opaque, and the transparent spaces between them serve as the slits. Newer photographic methods use interference from lasers to produce the pattern on photographic film. Then the film is processed to produce the parallel lines. A typical diffraction grating may have 10,000 lines per centimeter. So in previous chapter, we have learned that when coherent monochromatic light passes through a double slit, it produces a pattern of alternating bright and dark fringes on a screen located far from the slits, right? The bright fringes or maxima occur in directions for which the path length from slits to screen a whole number multiples of the wavelengths of light used. In these directions, light waves arrive in phase and interfere constructively. Three equally spaced slits would produce the same type of interference pattern for the same reason. Consider what happens when light of wavelength lambda passes through a large number n of equally spaced slits, as in a diffraction grating, as shown here in figure 2. The spacing between the slits is represented by W. For an angle theta equals 0, all of the waves arrive in phase with a maximum in intensity. This is the zero order maximum, which is the same for all wavelengths of light. The next maximum occurs at angle theta 1, where the path length difference between successive slits is exactly lambda. The waves are again in phase when they reach the screen. If you apply trigonometry to figure 2, you will see that path length difference, or delta L, is equal to W sine theta 1. The first maximum of intensity, called the first order maximum, occurs when this path is equal to 1 wavelength, according to this equation. Lambda equals W sine theta 1. This condition is exactly the same as the condition for the first maximum for the double slit. The result is constructive interference at an angle theta from each slit and the bright maximum in that direction. For each whole number m, the angle theta m must satisfy the following condition. M lambda equals W times sine theta m, where m equals 0, 1, 2, 3, and so on. This corresponds to a path that differs by a whole number multiple of wavelengths. Again, the waves arrive in phase at this angle and interfere constructively, resulting in a maximum called the mth order maximum. Here, m is called the order number. At angles between maxima, the waves from each slit differ in phase and interfere to produce relatively wide dark areas on the screen. The overall result is a pattern of extremely narrow maxima. Okay, here figure 3 compares the interference patterns for different numbers of slits. The same equation describes where the maxima occur for a single given slit separation, W. So the maxima are all at the same angle. As the number of slits increases, each maximum becomes narrower. Since the typical diffraction grating has thousands of slits, the maxima it produces are in precisely defined directions. In addition, since the separation between the slits is typically quite small, the maxima are widely separated from each other. So you can compare differences. If we have two slits, then the pattern should look like the graph here. As the number of slits increases, the maximum becomes narrower and more sharply picked. The resulting patterns of bright and dark lines are called diffraction fringes. Okay, next, let's have a look at the concept of using gratings as a spectrometer. When light of different wavelengths is incident on a diffraction grating, each wavelength produces diffraction peaks in different directions. This makes a diffraction grating a powerful tool for separating light of different wavelengths. So as you can see here, figure 4 shows what happens when a mixture of green and red light passes through a diffraction grating and then onto a screen behind it. The resulting spots on the screen are circular because the deflected beam is circular, which is shown here in figure 4b on the right. So as you can see here, red and green light diffract at different angles because they have different wavelengths, right? So according to this formula here, m lambda equals w sine theta m. So if w is fixed for different m, we have sine theta m equals m lambda over w, right? Because red light and green light have different wavelengths lambda. So their angles theta m for each of the m's order fringe could be different. As you can see here, these are the bright fringes, right? We have different locations here because we have different wavelengths. Okay, figure 4a also shows that the angles at which maximum occur have a simple and precise relation to the wavelength of the light. This behavior of the diffraction grating makes it a powerful tool for precisely measuring wavelengths of light. So based on the concept here, so spectrometer shown here in figure 5 is a device for measuring wavelengths of a light. Light from a source passes through the slit and into the collimator. A collimator is a system of mirrors or lenses that produces parallel wavefronts. The light then passes through a diffraction grating and onto a telescope. Telescope produces an image of the slit that appears as a line formed from the given wavelengths of light. The observer positions the telescope so that the crosshairs mounted in it fall on the slit image. The observer then reads the angle from the scale below the telescope. Since the number of lines per centimeter and therefore the line spacing for the diffraction grating being used is known, the wavelength of the light can be calculated from the measured angle. Astronomers use spectrometers to identify elements in space and on other planets. Okay, so based on what we have learned so far, I'd like you to try to solve this problem here, okay? So in this problem, we have a light with a wavelength of 440 nanometers is incident on a diffraction grating that has 8,500 lines per centimeter. And you calculate the angles of the maximum. All right, let's have a look at solution to sample problem 2. Again, we can use W equals 1 over N to determine the slit separation W. Then use the equation M lambda equals W sine theta M to determine the wavelength from W and given angle theta 1. So first of all, W equals the reciprocal of N, which is 1.111 times 10 to the power of -6 meters. For the first order maximum, we know M equals 1, right? Therefore, lambda should equal W sine theta 1 equals M, which is 5.89 times 10 to the power of -7 meters. So the light has a wavelength of 589 nanometers. Any questions? Okay, good. If no questions, that's the end of today's class. I'll see you next time.